So we are live. What I have decided that I will be doing linear algebra questions of MH set the year 2017. During that time, there used to be paper one, paper two, and paper three. Paper one preparation I haven't started yet. Inside paper two and paper three, it was like in paper two there is more of math, and in paper three there is more of stat type. But we are going to solve all the linear algebra questions from that particular year. Let's start with the question number 5 from paper number 2. Let A be an n cross n real matrix. Then what is determinant of A? Okay. So suppose if I just let it be like suppose if I just take a 2 cross 2 matrix like this. So I have the entries A, B, C, D. What I have to do is determinant of A is there multiplied with that. So it is being multiplied to each element of this, right? Determinant of A, determinant of A, determinant of A, determinant of A, right? So from the first row I can take it once out. From the second row I will take second times out, and what will be left is nothing but a determinant of A. So finally I will be left with determinant of A whole cube, right? So it should be n plus 1. It was a simple question but interesting one. Then what is A transpose? It is orthogonal, symmetric, skew symmetry, or not defined. First of all, my A is what? My A is a 2 rows, 3 column. Then what will be A transpose? A transpose will be 3 rows, 2 column. So the final output is nothing but going to be a 2 cross 2. So let me just find out the output by the way. So is it right? It is right, I think so. So it is 3, 1, minus 1, 0, 1, 2. 3 1 minus 1 0 1 2. So the first entry is 9, 10, minus 1 is 9, then 0 1 minus 2, that is nothing but minus 1, 0 1 minus 2 is nothing but minus 1, 0 1, and then it is 4, it is 5. But by the way, this is going to be a symmetric matrix. Is it an orthogonal matrix? How could I just find out is it an orthogonal matrix or not? I just need to multiply it with transpose, right? So this 9 minus 1 minus 1 5. If I multiply it with the transpose, it will be 9 minus 1 minus 1 5. If I just multiply this with this, it is not coming out to be 1. So it cannot be orthogonal. It is not skew symmetric. It is defined, so it should be symmetric. Okay, it was a simple question. The following system of the equation has a unique solution, has no solution, has two solution, has infinitely many solutions. Okay, good question. So what we know is I will write it in an augmented form, and what are the situations that may arise? So there could be three cases that may arise, right? So I just write those three cases. If my rank of A is equal to the rank of A augmented B, and it is same as the number of variable, that is nothing but number of variable, that is something 3, then it has unique solution. If my this two are same but this is not equal to the number of variable, there are infinitely many solutions. And if my rank of A is less than this, then there is no solution, right? So let's just think about this. Has two solutions. Let's see what can happen in this situation. If I observe it carefully, what I see is if I add this two, I'll get this, correct? So what I found is my rank of A is nothing but 2, correct? And after that, if I see about rank of A augmented B, it should be what should be rank of A augmented B? What I did is I just added this two and I got this. But in this case वो नहीं हो रहा है. So the rank of A augmented B will be 3. Since it is less than, it has no solution. It was a good question, by the way. Yeah. An orthogonal matrix, then what should be the determinant? About orthogonal matrix, we know that A into A transpose should be identity. So if we just consider the determinant, so it is determinant of A, determinant of A transpose, it is equal to 1. Now that means determinant of A square is equal to 1. That means it could be either plus 1 or minus 1. The minimal polynomial for this matrix is, okay, the good question, because minimal polynomial, we need to find out the minimal polynomial. Okay, so what we can do is we can try by one of the options. It's like, suppose if I consider A minus I, so it is what? A minus I is 0 3 minus 2 0 0 3 3 minus 2 and minus 2, correct? Okay. So this is wait. Wow, this looks great. There is something special. So this is nothing but this. Now what I do, I just consider a minus 2I also. Let me just consider this. So what will be this? This is nothing but minus 1. This will be as it is. This is 0. This is 2. This is minus 2. This is 0. This is 3. This is minus 2. So it is minus 3. Okay. Hey, wait a second. Can I make a square of this? Can I make a square of this? I can make the square of this, yeah. I can make a square of this. Let me just see the square of this. So if I just take a square, so it is square of this. So the first row, first column is 0. Okay. First row, first column is 0. Second row, first column. So these are zeros. So if I multiply this with the second one, do I get a 0? First row, second column. First row, second column. Is the answer 0? No, it is not 0. So this cannot be the minimal polynomial. Okay. But there should be some way. I might be missing out some particular way because I don't feel they must be asking it like in that sense. What can we do, buddy? Definitely 2 is imminent. Oh, what I can do is I can find out the eigenvectors, and then I can think of it. Okay, that might be the easier way. So what we do is we just try to find out the eigenvectors. So the eigen, what is this called? Characteristic polynomial. So it is minus of trace of it. So it is 4 times lambda square plus a11 क्या है? What is a11? That is nothing but a11 is nothing but determinant of 4 minus 2 3 minus 1. So this is nothing but minus 4 plus 6, that is nothing but 2. What is a22? A22 is nothing but I need to relate this. So it is 1 minus 2 0 minus 1. So it is minus 1. What is a33, my dear friends? It is a33 is 1304. So it is coming out to be 4. If I add these three numbers, it is 5 times lambda. Okay, and after that, last should be the determinant. So determinant is what? Determinant is nothing but 2 is equal to 0. So I put 1, yes, it is a root. If I put 2, if this is not 2 is definitely the root of it. If I put 2, it should be a root of it. Okay, so now I know 1 is one of the polynomial. So root of this polynomial. So what I'll do, I'll use a synthetic division. So क्या होता है? That is a syntactic division, right? So it is 1 if I put, it's 1 minus 4, 5 minus 2. So 1, 1 ones are 1, minus 3, 2, 2, 0. This is the equation. So lambda square minus 3 lambda plus 2 is equal to 0. What are the roots of this? 2, 2 square 4, 4 plus 2. Yes, it is a root. And 1, right? 1, 1, 1. So what I know is this is nothing but the characteristic equation. This is nothing but the characteristic equation, right? This is the characteristic equation. So the minimal should divide it. So if it is not this, it should be this. Okay. Now let's just check it out. C. So we just need to check about C. Nothing else. Wow. This became simple, right? Now this became simple. Need to erase this part. Uh, just now we found a minus I, and I now I will need a minus 2I also. So what is a minus I? It is 0 0 0 3 3 3 minus 2 minus 2 minus 2. And what is a minus sorry, what is a minus 2I? So a minus 2I, a minus 2I. Okay, let me just check. A minus 2I, so it is minus 1 0 0 3 2 3 minus 2 minus 2. What it should be? It should be what? Minus 2, right? So it is minus 3. Okay, let's just see the first row, first column is definitely 0. This is 0, 6 minus 6, so it is 0. And 0 minus 6 plus 6, so it is 0. Good. After that, second row, first column is 0. This is also 0. Second row, second column, so it is 0, 6 minus 6, 0. 0 minus 6 plus 6, 0. It should be like that because they are the same row, so it should be 0. It should be 0 because if I just multiply it will be the same because over here the rows are same. So option C is correct because it is satisfying, but it took too much time. That was not expected. If A is a 3 cross 3 matrix such that A cube is equal to 0 and A square is not equal to 0, then the Jordan canonical form of A is what? Okay, that is a good question, by the way. So I know my A raised to n, A raised to 3 is equal to 0. That means I somehow know that is nothing but a nilpotent matrix. Okay, and also if I observe this, I observe this. Uh, great. Jordan canonical form. So this is going to be the minimal polynomial. Yeah, yeah. This is going to be the minimal polynomial, right? So the minimal polynomial is what? Minimal polynomial is this. Therefore, for the zero, the Jordan block should have the dimension of 3. Correct. The power of a minimal polynomial gives us the power of the minimal polynomial gives us the size of the Jordan block, biggest possible size present in the Jordan canonical form, right? So I know the Jordan canonical form for 0 has a size 3, and based on it, the answer is this A, correct? Because this is nothing but a single Jordan block of size 3. Good question. If a real matrix A has a characteristic polynomial this and the minimal polynomial this, okay, good. Then which of the following statement is true? Okay. So what is about the trace? Trace of the matrix is nothing but the sum of the eigenvalues. So it is 2 plus 2 plus 1 plus 3. So it is right. It is. This is true. This is actually true. What is the determinant? It is nothing but 2 into 1 into 3. So sorry, it is 2 into 2 into 1 into 3. So it is 4 into 3. 4 into 3 is 12. So it is also true. It is diagonalizable over R or it is not diagonalizable over R. So we know that, okay. If the minimal polynomial is of the linear form, then it is always diagonalizable, right? So test diagonalizable is true. If the minimal polynomial is in the linear form, then it is diagonalizable, hence this is false. It is not. Okay. If the characteristic polynomial of the matrix A is nothing but this, and the minimal polynomial is this, and then the Jordan block for A, Jordan canonical form for A is what? Okay. So I know for A there will be 2, 1. Okay, and the maximum size of the block is 2. So it should be like either B or D should be correct. Let's see for the other one. There is 2, and the maximum size is 1. So it is from in B the size is 2. This size is 2. So this cannot be the correct one. So the option, this is right, option B. Now S and T are such satisfying, then which of the following statement? This is a dimension 2, T has a dimension 2, this vector space dimension 2, this is not a vector space, this is vector space. Okay, neither of them are the vector space. So first of all, we'll just show that which of them are the vector spaces. Definitely this is a vector space, this is a plane passing through origin. If you observe this cannot be the vector space. What if we, will it be a vector space? Buddy, let's just verify it. Suppose if I have two elements inside this, for an example, I consider I just consider 1 into 2, 1, 2, and minus 2. So this is nothing but 1, 2, and minus 2. Suppose if I just take a minus of it, if it is minus of t, I consider this is an element of t. I consider minus 1, minus 2, and 2. If I just you apply the condition in this, so it is 1 into 2 plus 2, which is not equal to 0. So this is not a vector space. Also, if I consider this, it has a dimension 2 because it is a plane. It has dimension 2. So S is a vector space of dimension 2, and T is not a vector space is the correct option. Okay, good question. Let's just go further. Let T from R3 to R2 be defined as T of XYZ be like this. The matrix representation of T with respect to the standard basis is what? Wow, good question. Um, so what I'll need is I will just need T of 1, 0, 0. If I observe it, it will be minus 1, 2. First of all, it will be of what dimension? It will be 2 cross 3, means 2 rows, 3 columns. So it is 2 rows, 3 column. Either B or C could be right. And from that, I know the first is this minus 2 and 1, minus 1 and 2, right? Yes. So option B is correct. Let T from R4 to R4 have the characteristic polynomial this. If T is diagonalized, then if T is diagonalizable, then the minimal polynomial of T is something. Oh no, it cannot be like this. I know that that was a result, one of the famous result. Let me just confirm this. Let me just confirm that result. The result is the matrix is sorry, the matrix is diagonalizable if and only if minimal polynomial. What about the minimal polynomial? If you know the minimal polynomial, then products a distinct monic linear factor. Yes, there was a result which I clearly remember. So definitely none of this is correct. If it is diagonalizable, this is not true. I got a doubt, so I just verified it. So now let's think about this. If it is diagonalizable, what does it? Oh, bare, yeah, bare. This is nothing but a dimension. This is geometrical multiplicity, right? This is nothing but geometrical multiplicity. Should be same as algebraic multiplicity. This is nothing but a eigenspace dimension, right? Ha! It was a good tricky. Let U and V be the vectors in an inner product space such that this and this is and this is there. Okay, so I think we are supposed to use that result U plus V square, I think, and then norm of U minus V square. It is equal to what? It is equal to 2 times of norm of u square plus 2 times norm of v square. So if it is 8 square is 64 plus this is 36, then it is 2 times of 7 square is 49 plus 2 times of norm of v ka square. Okay, that is fine. So this is nothing but 100 minus what it is. This is nothing but what it is 98 actually. So it is 2 is equal to 2 times norm of v square. So norm of v should be 1. Yeah, it was a good question. The eigenvalues of this matrix are okay. Let's just verify. How could I think about the eigenvalues, by the way? So one is there, 1 1 1 1 2 minus 3 3. Okay, so one is there, then I can think about it. Okay, so what I do, I just find out quickly the characteristic polynomial of it. So it is lambda cube minus stress is 3 times lambda plus this is square. Over here I should add the those things. So it is 1 plus a11 is 1. What is a22? I need to delete this too. So it is 1 again. If I delete this and this, what is left? That is nothing but 1 minus 4. That is nothing but minus 3, right? So it is minus 3. Okay, so it is minus 3 times lambda. Again, if I just see the determinant is nothing but 1 minus 3. It should be minus 3, right? Because if I just take this column, it is totally fine. I just need to take care of the alternating sign, right? Yeah. So if I just consider this is nothing but 1 and then minus 2 times minus 2 and then it is 2 minus 4. Yes, so it is minus 3 is correct. This is equal to 0. So the characteristic equation will be lambda cube minus 3 times lambda square minus lambda plus 3 is equal to 0. I know one of the root is 1, so it is 1 1 minus 3 minus 1 3, so it is 1, it is 1 minus 2 minus 2 minus 3 minus 3 0. So it is what is left. So it is lambda square minus 2 times lambda minus 3 is equal to 0. So minus 3 should be divided into two parts, so that answer is minus 2. So it could be minus 3 times plus 1. So the roots are 3 and 1 or minus 1. It is minus 1. So option C is correct. Right, a good question. Let M be the square matrix with real positive entries such that each columns add up to 1. Then which of the following statement is not true? An eigenvalue of M is 1. Yeah, if the square matrix with real positive entries such that each columns add up to 1, which of the following is not true? This is true. Whenever the column add to the same number, that is going to be one of the eigenvalues. The sum of the entries of the eigenvector corresponding to the eigenvalue lambda not equal to 1 is 0. Why it should be there is no eigenvalue this such that value. Oh no, the sum of the entries of the eigenvector corresponding to the eigenvalue 1 is 0. The sum of the entries of the eigenvector corresponding to the eigenvalue 1 is 0. If the real matrix entry says that the columns add up to 1. Okay, so what I know is, suppose this is a 3 cross 3 matrix, such that the columns add up to 1. This add to 1, this add up to 1, this add up to 1. So 1 is going to be one of the eigenvectors. This is true, definitely. The sum of the entries of the eigenvector corresponding to the eigenvalue lambda which equal to 1 is 0. Okay. By the way, I don't know about this. There is no eigenvalue lambda which is not equal to 1 such that the norm of it is greater than equal to 1. Oh, this is going to be a troubling question to us, buddy. Yeah, the eigenvalue lambda is not equal to 1, such that, okay, the sum of entries of an eigenvector corresponding to eigenvalue 1 is 0. Suppose this is nothing but an eigenvector xyz, and then since the eigenvalue is 1, so it is xyz. The sum of the entries of an eigenvector corresponding to eigenvalue 1 is 0. So let us just verify this. So from this, what I know is, suppose I give them the name A1, A2, A3, B1, B2, B3, C1, C2, C3. From the equation, I have A1 x plus B1 y plus C1 z is equal to x. Uh, what I know is A2 x plus B2 y plus C2 z is equal to y. A3 x plus B3 y plus C3 z is equal to z. And if I add all the equation on the side, what I get is I get x plus y plus z is equal to x plus y plus z. Is it true? X plus y plus z is equal to x plus. So there is no use of it. I should be able to do something else. The sum of the entries of the eigenvalues corresponding to the eigenvalue 1 is 0. Let me just check it here. If I add this, this will become 1, this will become 1, this will become 1. So I get left hand side is same as right hand side, it is of no use. The sum of entries of the eigenvector corresponding to the eigenvalue 1 is 0. I need to show that my x plus y plus z is equal to 0. I don't think so. I don't think so. This is going to be a good question. This is a good question for the moment. Let me just check if there is any other question left after this. So yes, there are some questions. I'll just come to this after some time. Because this is from part 3, it might be stat related questions. In stat subject related, nahi hai, lekin still it is a good question. Let M be a real symmetric positive matrices n cross n. Which of the following statement is false? Okay, there is an n cross n determinant of, okay, which time it is unitary. Okay, M is a real symmetric positive definite n cross n matrix. Which of the following statement is false? The determinant of M is positive. Since all the eigenvalues are positive, the determinant should be positive. It is always diagonalizable. It is a symmetric matrix, so it is always diagonalizable. A real symmetric with a positive definite is a unitary matrix. Unitary means what? It means A into A transpose, which should be equal to identity. It may not be true. There is an invertible matrix P such that M is equal to P transpose P. Why is it so? Why is it so? देखो, I feel this is false. It may not be unitary. For an example, suppose if I give you some other matrix like 1, 2, right? So this is a real symmetric matrix which is positive definite, which is not a unitary matrix. So this is false for sure, right? So the correct option is D. So what I learn is there exists an invertible matrix P such that, and this I have read somewhere, but I'm unable to recorrect it. But the statement is true. M is equal to P transpose P. Okay. Find the matrix of the linear transformation of a derivative with respect to the basis. This, oh, good question by the way, and the last question. But still, we have to discuss this question also. But the matrix of the linear transform and derivative map. Okay, with respect to this basis. Oh, that is cool. Actually, too much cool. Okay, so what I do is I will just find out my, suppose I give this name as a T. This matrix has been given the name as T. So my T of B1 will be what? It is derivative of it. So it is 2 times T plus 1. So I should be able to write this 2 times T plus 1 into the form of B1, B2 and B3. That is something strange, poda, right? Body. Okay, what I see is from this I will just choose one of them. So is it adding all of them? No, adding all of them won't work. This all zero won't work. So this 100 is also not working. So this should definitely work. So what I observe is the first in the minus, and this is in the okay. So it is like b1 in minus plus b2 plus 0 times b3. It works, I think. If I just consider b2 minus b3, so this get cancelled, then this is 2 times of this, and this, yeah, it is working. It is working. So the B option is correct. It was a cool question, but over here we came. Let M be the square matrix with a real positive entities such that the columns add up to 1, then which of the following statement is not true? I have just have to think about B, C, or D. The sum of the entries of an eigenvectors corresponding to an eigenvalue is 0. The sum of the entries of an eigenvector corresponding to eigenvalue should be 0. There is no eigenvalue lambda which is not equal to 1 such that there is no eigenvalue lambda not equal to 1 such that. Okay, so what I can do is, my dear friend, okay, that means they are trying to tell us that the only possible eigenvalue is something which is lesser than modulo 1. So let me just think about this option C for the moment. There is no eigenvalue which is not other than 1. There is no either value other than 1 such that mod of this is less than greater than equal to 1. So what I do, I just try to create something 1 by 2, 1 by 2, 1 by 2, 1 by 2. So this is nothing but a matrix such that the columns add up to 1. So if I just consider this matrix, I think this is going to be one of the projection matrix. So iska square karte hain. Let us just do the square of this. If you just square of it, it will be an identity, because if I multiply this with the first, it is half into half. No, it is same thing. So it is half into, it is the same thing, yeah. So it is half, 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 half. Like, so that means my p square is equal to p. Therefore, p square minus p is equal to 0. Therefore, 1 and the 0 are the eigenvalues. The sum of the entities of an eigenvector corresponding to the eigenvalue 1 is 0. Okay, what I can do is, in this case, I'll just find out the eigenvector corresponding to this. Okay, so I'll just find out eigenvector corresponding to this. So this is nothing but half, 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 half. Over here, I'll just use xy, and it should be the 1, so it is xy. So that is nothing but half x plus half y, half x plus half y is equal to x. So if I just take to the other side, so I got x is equal to y, correct? And in the other case also, if I consider half x plus half y is equal to y, then this goes to other side, so x is equal to y. We get it. So it is 1 comma 1 is one of the eigenvector, right? This 1 comma 1, yes, it is 1 comma 1. If I just apply, it is half times half plus 1, yeah. So the sum of the entries of an eigenvector corresponding to the eigenvalue 1 is 0. This is nothing but a wrong statement, so this is nothing but false. Okay, so good question. It troubles us, but what are the things that we learn is the sum of the entities of eigenvector corresponding to the eigenvalue is 0. Okay. If for other than that, it is 0. Okay, otherwise not. Okay. Arey yaar, it was so simple. It was so simple. This is true. This is true. Actually, I just proved it after before some time. It should have been 0. Otherwise, there is no choice. Wow, this is true. Then this would be, there is no eigenvalues is such that, also from that statement what I understood is this is equal to this. It means eigenvector should be 0. Okay, this is a good question, by the way. How to learn a lot. Okay, so let's just count it, and I'll just write down the how many questions that we solved. Um, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16. 16 questions were there. Okay, so I had great fun solving this question. Thank you so much, guys, for